Here we see an unsorted list of data. It's got 5 different sets, 5 different pieces of data. You may wonder why it starts at 0 and ends at 4. Well, it's because Python and other popular programming languages are 0 indexed, meaning it starts at 0 and ends at 1 less than the actual length of the data set. So the first thing a computer will do in a bubble sort is it'll check this first number, this second number, so that's index 0 and 1, and to see whether 4 is smaller than 1. Well, obviously it isn't, so it moves on to the next pair to see whether 2 is smaller than 4. Well, obviously it is. So they'll take this 2 value and they'll move it into temp. Temp is a variable which changes every time it swaps. 4 is then moved from index 1 to index 2, and 2 is moved back from temp into index 1. It'll then check whether 4 is smaller than 5. Well, obviously it is, so it moves on to the next pair. It'll then check whether 3 is smaller than 5. Well, obviously it is, so it'll change them. It'll move 3 into temp, and then 5 into index 4. 3 then gets moved back from temp into index 3. And then that's called a full pass. That's a pass. It'll then move on to the next pass, provided that the data set isn't sorted. So it'll check index 0 and index 1, and obviously they're sorted. It'll then check index 2 and index 3. Well, they're not sorted, so 3 gets moved into temp, 4 gets moved into index 3, and 3 gets moved back into index 2. 4 and 5 are obviously in the correct place. And then it'll do a checking pass. So that was the second pass. The third pass will check whether 1 and 2 need swapping. They don't. Check whether 2 and 3 need swapping. They don't. Whether 3 and 4 need swapping. They don't. And whether 4 and 5 need swapping. They don't. That means that the list is fully sorted. It can then return the list to the user. The problem with this is that it's very inefficient because it has to check every single pair, and while you can make it more efficient because every single pass, the only number that you can be sure is in the right place is this last index, this index 4, or whatever your last number is. That's the only one you can be sure is correct after each pass. So this means that as efficient as it can get, it's still only doing 1 less each pass. That means for data sets like this, that was 1 nearly sorted and 2 very small, it's suitable because it's easy to code and very memory efficient because it uses in-place swapping, which means that it doesn't take up which means that it replaces the list that it had already been working on, which makes it use less kind of memory, which in times when memory is at like a very low quantity and it's hard to get much of it, it's a very useful swap. Things like the quick sort don't use that and so aren't very memory efficient. But whilst it has its time and a place because it's very easy to code and for nearly sorted data sets it can stand up with the rest of them, for larger data sets it starts to become very inefficient and very slow.